Hi all. In this class we can see what is a binary symmetric channel and how we can find the capacity of a binary symmetric channel. So a channel means it is the medium through which we are sending our information from sender to the receiver. And this binary symmetric channel is also a special case of the discrete memoryless channel with two input and two output. That's why it is called binary channel. So why it is called symmetric channel means the probability of receiving 1 if 0 is sent is same as that of the probability of receiving 0 if 1 is sent. That means if we send a 1 then we got a 0, then the probability of getting that same as that of if we send a 0 then if we got a 1. So that probabilities are same. That's why it is called symmetric channel. So we already studied that for a symmetric channel, by looking the channel matrix we can identify whether it is a symmetric channel or not. So for a symmetric channel, the transition matrix first row of elements should be repeated in the subsequent rows, and the placement of that elements only different in that case, in case of a symmetric channel. So here also we can say that for a binary symmetric channel we have only two rows, and the first row element repeated in the second row element, but the position of that elements should be different. So that's why it is called symmetric channel. So we have only two input symbols. We can take it as x1 and x2. x1 represent the input 0 and x2 represent the input 1. Similarly, we have two output symbols y1 and y2. y1 represents 0 output and y2 represent 1 output. So this for any channel we can represent the input output relationship using the channel matrix. So here also we are using the channel matrix to represent the input output relation, and in that the conditional probability of error is denoted by p. That means the probability of getting 1 if we send a 0 is represented as p. Similarly, the probability of getting 0 if we send a 1 is also represented as p. That is, the probability of a bit flipping is represented as p. And we can see the transition probability diagram here. So in that we can see that we have two input x1 and x2. x1 represent a 0 input and x2 represent a 1 input. And we have two outputs, y1 and y2. y1 represents 0 output and y2 represent 1 as the output. Then we can see that the transition from x1 to y1 is represented as 1 minus p, and the transition from x1 to y2 is represented as p. Similarly, the transition from x2 to y1 is represented as p, and the transition from x2 to y2 is represented as 1 minus p. That means the probability of getting 0 if we send a 0 the same as that of the probability of getting 1 if we send 1, and that is represented as 1 minus p. Similarly, the probability of getting 0 if we send a 1 is same as that of the probability of getting 1 if we send a 0, and that is represented as p. So using this diagram we can represent our channel matrix. So the channel matrix is represented as p of y by x. So first element is represented as p of y1 by x1, and second element is p of y2 by x1. And the second row first element is represented as p of y1 by x2, and the second element is p of y2 by x2. So we can see that in this figure the p of y1 by x1, that means the probability of getting output y1 if the input is x1 is represented as 1 minus p, and p of y2 by x1 is represented as p. Similarly, p of y1 by x2 is represented as p, and p of y2 by x2 is represented as 1 minus p. So this is our channel matrix, and this is our channel diagram. So we can see in this channel matrix that the first row element is repeated in the second row, but the position of first row element is different that of second row element. So that's why it is called symmetric channel. So next our aim is to find the equation to find the capacity of this binary symmetric channel. So for that again we are considering our channel diagram. So the channel diagram we can see that x1 to y1 transition is represented as 1 minus p. This 1 minus p we can also called as p bar. And from x1 to y2 and x2 to y1 it is represented as p, and x2 to y2 is represented as 1 minus p or p bar. Then the probability of x1 is represented as w, and the probability of x2 is represented as 1 minus w or w bar. And similarly we have the output y1 and y2. So we can say that p represents the probability of error, that means probability of reception of 1 when 0 is transmitted, or probability of reception of 0 when 1 is transmitted. So simply p means the probability of error. Then p of x1 we took as w, p of x2 is 1 minus w or w bar. So the symbol x1 is encoded as 0 and the symbol x2 is encoded as 1. So we can see in figure. Then we can write the channel matrix. We already said that the channel matrix is 1 minus p, 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 1 minus p, and this 1 minus p we can also represent as p bar. So we will get the channel matrix as p of y by x equal to p bar, p, p, p bar. This is symmetric matrix because both row contain same element in a different order. So for a symmetric channel we already found what is h of y by x. So h of y by x equal to h, which is equal to summation of j equal to 1 to s pj log of 1 by pj, because it is a constant which remains same for all rows, since all rows consist of same elements as that of first row. So we already derived the expression for h of y by x for a symmetric channel, so you can refer that. So remember that h of y by x is equal to summation of j equal to 1 to s pj log of 1 by pj to the base 2, and which should be a constant for a symmetric channel. So next we can see what is h of y by x for a binary symmetric channel. So here binary symmetric channel means we have only two symbols, so the j varies, j changed from 1 to 2. So we can write h is equal to summation of j equal to 1 to 2 pj log of 1 by pj. So pj, if you are taking j as 1, you will get it as p1 log of 1 by p1 plus p2 log of 1 by p2. So here p1 is p bar and p2 is p. So we can write it as p bar log of 1 by p bar plus p log of 1 by p. Then next we can find entropy of output symbol h of y. So h of y is equal to summation of j equal to 1 to 2 p of yj log of 1 by p of yj to the base 2. So we can replace j as 1 and 2. So you will get it as p of y1 log of 1 by p of y1 plus p of y2 log of 1 by p of y2 to the base 2. So next we need to find what is p of y1 and p of y2. Only we know the input probabilities are w and w bar. So we need to find the output probability. So to find the output probability, we can easily found this using the total probability theorem. So the total probability theorem says that p of y1 is nothing but p of y1 by x1 into p of x1 plus p of y1 by x2 into p of x2. So p of y1 by x1 into p of x1 plus p of y1 by x2 into p of x2. So we can see p of y1 by x1 is p bar and p of y1 by x2 is p. So we can replace that. So p bar into p of x1 we took as w plus p of y1 by x2 is p. Then p of x2 is w bar. So you will get p of y1 as p bar w plus p w bar. Similarly, p of y2 is equal to p of y2 by x1 into p of x1 plus p of y2 by x2 into p of x2. So p of y2 by x1 is p and p of y2 by x2 is p bar. So we can replace that. So you will get it as p w plus p bar w bar. Next we can replace this in h of y equation. So you will get it as p bar w, p of y1 changed as p bar w plus p w bar log of 1 by p bar w plus p w bar plus p of y2 is changed as pw plus p bar w bar into log of 1 by pw plus p bar w bar. So next we can find the mutual information of a binary symmetric channel. So after getting this h of y and h of y by x, we can easily find the mutual information. I of y comma x is equal to, which should be equal to I of x comma y equal to h of y minus h of y by x. So we can write the h of y expression minus h of y by x expression. So h of y expression is p bar w plus pw bar log of 1 by p bar w plus pw bar plus pw p bar w bar into log of 1 by pw plus p bar w bar minus h of y by x is y by x is p bar log of 1 by p bar plus p log of 1 by p. So this is the mutual information of a binary symmetric channel. So next we can see the capacity representation. So for a symmetric channel, the capacity representation C is equal to log s to the base 2 minus h, where s represent the number of symbols, and this representation is for 1 message symbols per second. That means the capacity with R is equal to 1 message per symbol. So we can find C is equal to log s to the base 2 h bits per second. And here number of symbols are 2, so log 2 to the base 2 minus h. So you will get it as 1 minus h. H is 1 minus p bar log of 1 by p bar plus p log of 1 by p bits per second. So that's the capacity of binary symmetric channel. Next, we can also find this capacity using the maximum mutual information. So we know that the maximum mutual information will get when the input symbols have equal probability. So we are taking our input symbol probability W and W bar equal to half. Then we are replacing this information W and W bar with half in this h of y expression. So you will get it as 1. After replacing that, so you will get again 1 minus p bar log of 1 by p bar plus p log of 1 by p. So that's also the same as that of capacity equation. So we can say that when the input symbols become equal probability, the mutual information should be maximum and become equal to the channel capacity C. So see, we can summarize that the binary capacity of the binary symmetric channel is C is equal to maximum of mutual information. So that is equal to 1 minus p log of 1 by p plus 1 minus p log of 1 by 1 minus p, or we can say that C is equal to 1 minus h. So this represents the capacity of a binary symmetric channel. Next we can see the graph between the capacity of this binary symmetric channel and the probability. So from this expression we can see that if the capacity when the probability is equal to 0, we will get the capacity as 1. So when p is equal to 0, we will get it as this term p log of p, and 1 minus p log of 1 minus p becomes 0. So you will get the maximum capacity is equal to 1. And when the probability is half, you will get the capacity as minimum. You replace this expression with half, so you will get the minimum probability as 0, minimum capacity as 0. And again, if the probability is maximum, then you will get again the maximum capacity. So we can we have two observations from this graph. And that means when the channel is noise free, permitting us to set P equal to 0, the channel capacity C attains its maximum value of 1 bit per channel use, which is exactly the information in each channel input. At this value of P, the entropy function h of P attains its minimum value of 0. That means h of P means the small h attains minimum value of 0. Then the second point is that when the conditional probability of error P is equal to half due to channel noise, the channel capacity C attains its minimum value of 0, whereas the entropy function h of P attains its maximum value of unity. In such a case, the channel is said to be useless in the sense that the channel input and output assume statistically independent structure. So we say that when the probability is P is equal to half, that means the probability of error P is equal to half, the channel capacity becomes 0. So that case we can't use this channel for transmission purpose, because the entropy function h of P or this h, small h should be maximum at this value. So these are the observation we can make from this graph. So that's all about the binary symmetric channel.